Hello doctor, my name is THANUSHAN son of SUBRAMANIAM. My matrix number is 251062107. Today me and my teammate will presenting a robot-like mechanism for the EMJ26703 design of machinery assignment 2. So the primary objective of this assignment was to design a robot-like mechanism capable of floor travel by walking or running motion. To achieve this, the mechanism was entirely developed using Autodesk Inventor to ensure precise control motion without relying on strictly prohibited wheel or roller assisted system. So first, this is our chassis part, the foundation of this design, which acts as the fixed ground link for our planar 4-bar mechanism. It was modeled as a rigid rectangular base in the CAD software. So as we can see here, I chose the slot center to center shape to create this part, then make 2 holes for 8 mm diameter. Precisely measured through holes were extruded at both ends to serve as the secure mounting pivot points for the moving component, ensuring the entire assembly remains stable during operation.
Hi, I'm PRAKASH, son of MAHENDRAN. My matrix number 251062092. Next, we have a crank, which is the green component functioning as the primary input driver. It was extracted as a short, durable link designed to withstand the rotational force from the end input auto. For the build this design, I used the slot center to center, and I put the hole as 8 mm. It was deliberately calculated and sized as the shortest link in the system to allow a full unobstructed 360-degree continuous rotation without colliding with the chassis.
So the next part is the rocker, which is in the red component, which acts as the follow link in our mechanism, modeled similarly to the crank but with an extended center to center hole distance. It is structurally constrained to oscillate back and forth. This oscillating motion is crucial because it controls the physical trajectory of the leg, enforcing the necessary lifting action during the recovery phase.
The main coupler of the system is main leg, usually represented by the great triangle plate. The top of verticals of the plate featured pinholes that met directly with the crank and holes. For build the design, I used the line for triangle and used the extrude means thickness of the software language for the 5 mm, and using the fillet for this one as a leg. I was using fillet 2 mm for this one. The extended bottom fetters was rounded off to act as the physical foot. Tracking by complex, repeatable part recover to make contact with the floor and propel the robot forward.
So all these components were integrated into the final 3D drawing. This is our final 3D drawing, utilizing a mirror dual linkage architecture to prevent lateral twisting. So this is the main leg, this is our crank, this is our rocker, and then this is our chassis. We can see at another side also we can see the same component, which is the main leg, the rocker and the crank. To validate the design, I conducted a dynamic kinematic simulation by applying a continuous rotary drive to the crank. Okay, when we move the crank, it will move. By continuously rotating the crank, the simulation perfectly demonstrates the authentic walking cycle, translating a simple rotary input into a forward stride on a clean lifting and recovery, proving the mechanism functions smoothly without any mechanical lockups. Also, if we change the position, you can see here. So we can clearly see the mechanism functions smoothly without any problems, without any mechanical lockups.
Finally, we moving to the 2D drawing. All components and the final assembly were carefully documented to show the all immovable dimensions. This is the top view from the 3D view. This is the side view from the 3D view. This is a front view from the 3D view. The exact measurement verified that the maximum extension, the assembly is 80.69 length, then 7 cm width and 8.37 cm height. This strictly satisfies the most critical physical specification of the assignment, keeping the entire footprint well below the maximum restricted bounding of the 0.5 max length times 0.5 width times 0.5 height. In conclusion, this project successfully translates a theoretical kinematic concept into a fully functional and vertical 3D CAD model. We achieve a stable 1 degree of freedom working mechanism that adheres to the all requirement design parameters and the volumetry limits. Thank you for your time, and that concludes the detailed breakdown of the robotic leg design. Thank you.